I mentioned in the introduction to this course that deformation of a member can be characterized as size change and shape change. Size change is characterized by the parameter normal strain, denoted by the Greek letter epsilon, and the shape change is characterized by the parameter shear strain, denoted by Greek letter gamma. Now let's look at the definition of these two strains. For a member before deformation, let's draw a random axis on it, axis n. Along this axis, there are 2 points, and the length between these 2 points along this axis is delta S. After deformation, if we look at the original axis n, it has been deformed this way into axis n prime. And the distance between the same 2 points, again along this deformed axis n prime, has a new length of delta S prime. When the original length delta S approaches 0, the 2 points approach the same point, and the normal strain at this point, defined specifically for the orientation along the axis n, is epsilon equals to the new length delta S prime minus the original length delta S, and then divided by the original length delta S. Since the numerator and the denominator both have units of length, the normal strain is dimensionless, or it can have the unit of length over length, which essentially is still dimensionless. Since epsilon indicates the change in size, a positive normal strain indicates elongation, and a negative normal strain indicates contraction. For shear strain, again, on this member before deformation, let's draw a pair of axes n and t. N stands for normal and t stands for tangent, and these two directions are always perpendicular to each other. Along these two axes, there are 2 short lengths on the member. After deformation, the original n and t axes have both been deformed, and the 2 short lengths have deformed along with them, and now this angle has changed into theta prime. Again, when the 2 short lengths approach 0, the shear strain is defined for their point of intersection to be gamma nt equals to half a pi, which is the 90-degree right angle written in radian, minus the new angle theta prime. The subscript nt for gamma indicates that this shear strain is specifically defined for the orientation of the nt axis. In other words, at the same point, the shear strain will be different for a different orientation. The angles here are both in radian, which is dimensionless. Therefore, shear strain is also dimensionless. And the shear strain simply describes the change in the right angle. If gamma is positive, that means the angle has become smaller, and if gamma is negative, that means the angle becomes larger. So now we have the definition of the normal strain and shear strain. If you recall, we have learned the state of stress for a particle. For the general 3-dimensional state of stress, we can fully characterize the state of stress by 6 stress components, 3 normal stresses, sigma x, sigma y, and sigma z, and 3 shear stresses, tau xy, tau xz, and tau yz. And for the planar state of stress, we have 2 normal stress components and 1 shear stress component, overall 3. Similarly, for an undeformed particle represented by this rectangular element, it has 3 original lengths, delta x along the x direction, delta y along the y direction, and delta z along the z direction. And within the xy plane, all angles are right angles, half a pi, same for the yz plane, and same for the xz plane. The deformation of this particle can also be fully characterized by 6 strain components, 3 normal strain, epsilon x, y, and z that describe the size change along the x, y, and z axis respectively, and 3 shear strains, gamma xy, gamma xz, and gamma yz that describe the angle change within the xy plane, xz plane, and yz plane respectively. Therefore, after deformation, this element will have new size 1 plus epsilon x multiplied by the original length delta x for the length along the x direction. New length 1 plus epsilon y multiplied by the original length delta y for the length along the y direction. And new length 1 plus epsilon z multiplied by the original length delta z for the length of the side along the z direction. If you say this is not quite along the z direction, well, don't forget that this is a particle with infinitesimal sides, and all the normal strains and shear strains are very small. Therefore, this approximation is good enough. And also, there are angle changes within the xy plane. The right angle has now changed into half a pi minus gamma xy being the shear strain associated with the xy plane. Same thing for the yz plane, and then same thing for the xz plane. And now the size change and the shape change of this particle has been fully characterized. Similar thing for 2D planar analysis. The particle is represented here by a rectangle with the side delta x along the x direction and delta y along the y direction. And this angle right here associated with the xy plane is half a pi, the right angle. After deformation, it will have new length along the x direction, which equals to 1 plus epsilon x multiplied by the original length delta x. Epsilon x is the normal strain along the x direction. New length 1 plus epsilon y multiplied by the original length delta y. Epsilon y is the normal strain associated with the y direction. And then a new angle, half a pi minus gamma xy. Gamma xy is the shear strain associated with the xy plane. And the size change and shape change of this element has been fully characterized by 3 strain elements. Here are several notes. First of all, as I mentioned, normal strain and shear strain are normally very small, on the order of a thousandth. And therefore, approximation and simplification are often used for the strain analysis. And just like stress, normally strain, it varies with location as well. And both stress and strain are subjected to the orientation of the particle. Later in this course, we will learn about stress transformation and strain transformation, which enable us to calculate the stress and strain at different orientations. Let's look at this example. There are 2 rods supporting a crate, and the initial position of the rods as well as their lengths are given. If the ring has been pulled to a displacement of 5 mm straight down, we need to determine the average normal strain in each rod. This problem is quite straightforward. We know the initial length of the 2 rods, so to find their average normal strain, we only need to find out their new length after deformation. So we need to do a little geometry. We're going to use these 2 right triangles to help us with some dimensions. According to trigonometry, we can calculate the length AD and CD, the length CF, as well as the length BF. Now, after deformation, keep in mind that the supports point A and B would not change. Therefore, the length AD and the length BF would not change. But the ring has moved to a new position C prime, which is 5 mm straight down from the original position. Therefore, now we draw 2 new triangles, and we can simply calculate that the new length C prime D equals to length CD plus an extra 5 mm, which is 0.005 meter, and we get the new length C prime D. We can do the same to calculate the new length C prime F, which is the original length 0.6 meter plus an extra 5 mm. Therefore, we marked the new length we calculated onto these two new right triangles, and simply by applying Pythagorean theorem, we can calculate the new length AC equals to 1.00339 meter, and the normal strain is defined as the new length minus the original length divided by the original length, and that equals to 3.39 times 10 to the negative third power. As you can see, it's dimensionless. So that is the average normal strain in the rod AC. Same thing for rod BC. By applying Pythagorean theorem again, we have the new length BC is 1.20231 meter, and then the normal strain is the new length minus the original length divided by the original length, and that is 1.92 times 10 to the negative third power, dimensionless. That is the normal strain in the rod BC.